This presentation is about the paper Mixing Up the ML Module System by Andreas Rossberg and Dreyer, written in 2013. So let's go over the background and motivation for this paper. This paper is mostly concerned with the concepts of ML modules and Mixin modules, and both of which are mechanisms for modular programming. This paper chooses these two module systems specifically because of their complementary pros and cons. As you see, ML modules are hierarchically composable, and they're easily able to hide implementation details and to express abstract data types. However, you cannot have recursively defined modules in the current ML module system, and you can't have the separate compilation for these recursively defined modules. And this is where mixin modules come in. Mixin modules do allow recursively defined modules, and within these recursively defined modules, different components can be separated and separately compiled. And this is a big component that is missing from ML modules that these researchers wanted to implement. So they decided they can take ML modules and Mixin modules and combine them to create MixML modules. And it's supposed to be a combination of the two that don't sacrifice the core semantics of either module system. So the main idea of MixML is to unify ML structure and ML signature languages into one language. So in ML, there are structures and signatures. Structures contain definitions, for example, your function implementation details. And then there are signatures, which contain specifications. For example, the type signature of your function, or there's new types in general, the types of values. And in ML, these definitions occur only in modules, or structures as they're called. Whereas in MixML, modules can contain definitions, specifications, or both. And one of the main motivations for combining structure and signature languages is that the language can be simple and regularized. For example, via only a single encoding, MixML can support hierarchical structures and signatures, as well as recursive structures and signatures, rather than having to have different encodings for structures and signatures. So this is just some basic syntax that's used within the paper when describing MixML. I'm not going to be going over all the syntax here, but this is just for reference for later on. I will be describing the syntax as we see it going forward. So this is an example of some basic syntax in action. So you start off with just an empty set, which is an empty module. It has nothing in it. And if you want to add a component, then you add the name of the component, which is L, and then the definition or whatever expression, signature, whatever you have, which is M or mod. And what this does is it has the exports and imports of mod are now the exports and imports of this whole module as well. Except now you access them using L dot and then whatever you need to put. And this is just a basic example of hierarchical composition or a namespace organization. And below you have some just basic definitions or specifications you might see in an ML language and how that would translate into MixML syntax. So here you just have a type definition or a variable declaration. Here you have a variable definition with an actual expression. Here you just have a type declaration, and then here you have a type definition. And this is what it would all look like. This represents a list of kinds that end up being the type. And then here you have a list of kinds, which equates to this type, which becomes a lambda expression for the type list of kinds. So with the syntax out of the way, we can start talking about some actual features. So for the first feature will be linking, which is pretty important in any module system. The first thing we go over is the syntax, which is you have x equals mod 1 with mod 2. And that's how you link mod 1 with mod 2. Now what this does, it will perform a mix-in composition of mod 1 and mod 2 in the style of Braca's merge operator, which is detailed below. What all it does is it combines the exports, which have to be two disjoint sets, and then it'll combine the imports and remove any exports to make sure that imports and exports don't coincide, which they should not. And one thing to note about this syntax is that mod1 is evaluated first and then put into the variable x prior to mod2 being evaluated. And what this allows is you have x as a representation of mod1 within mod2. So now you can access any members of mod1 using the variable x if you need it. And we'll see later why this comes in handy. The paper also recognizes that for linking, two modules should be compatible with each other. So it provides this definition of compatibility where for linking modules M1 and M2, you just want to check component by component whether the two modules are compatible. So all you have to do is that for each component which has the same path name in both modules, these conditions must hold. C must not be a term export in both modules, so there cannot be a value of a variable, because overriding is deliberately excluded in this module system. They left that to the whole object-oriented people to work with. They don't really care about that. And if C is an import of M1 and an export of M2, then M2's export must match M1's import specification. And the same is true if you reverse the import and export roles. And all this is saying is that just if one imports the other, then they just have to match in type basically. If C is a type import in both modules, then they have to be specified as the same kind of type, and the same if there's exports. And if C is a term import in both modules but have different types, then one of them must be a subtype of the other. And then when you get that new module as a result of linking, the stronger type is used as the new type in the specification. So for having a recursively defined module, which means that the module sometimes has to refer to itself, you can do that very easily with basic linking because of the way linking is defined. So all you need to do is have two modules, one that has the specification and one that has the definition. And this is equivalent to having like a signature and a structure in basic ML. And once you have these separate modules, as we discussed earlier, the first module goes into the variable x. In this case, its own specification is in the variable x. So the definition can refer to its own components recursively using the variable x. And this is one key aspect of MixML, that the recursive structures are very easily defined with the linking method. In fact, the linking method is just a generalization of recursive definitions. One important feature we want from ML modules is the ability to easily express abstract data types. In MixML, this is addressed by opaque linking. It's very similar to linking, but you have seals instead of with as the keyword. And the program only sees information in mod 1, not mod 2, when you're doing it in this syntax. So what this means is if you want to have a data type which is specified in a module, and you want the implementation details to be hidden, then you make a signature which only has the type information that the user might need, and then you can seal the module behind the signature. And this is equivalent to in ML syntax having a module hidden behind the signature. And this is how we define abstract data types in MixML. A key feature of module systems in general is functors. Functors are like modules, but they take another module as an argument. And based on the argument, then the result can be something different. For example, like a tree map or a hash map can be an argument, and based on whichever kind you pass in, there's a different operation. So in MixML, functors are implemented as units, and a unit is written with square brackets on the side, and that is just a suspension of the module. So that means that you can access its components. It's like a reference to the module. And functors are written as units, and they have two components, an argument and a result. And you'll notice this little x, not x, you'll notice this triangle next to the x. And what that means is that x is a local binding used within the module, and arg is the external binding. So that's what you would refer to when you were trying to access the component from outside the module. So once you have this overall functor here, you can bind that to a variable f. So this whole thing would be f. And so if you want to apply it with an argument, you would have, this is what the syntactic definition would look like. You would have an argument mod, and what this will do is it will merge with the existing functor. So this becomes the actual arg that we see in the functor. And then with the new f, we'll instantiate the functor basically. So that's what that does. And then once you link those modules together, then you'll have the result. That's what you're doing with the dot result here. You were just getting the result out. You were getting the result of the functor. And that is how Mixml implements functors, very cleanly and simply. So we saw units being used for functors, but we can also use units to help with separate compilation. Separate compilation is a big feature that the Mixml authors wanted, so this is a pretty important aspect of the paper. So what they do with units is, let's just run this through by example. We have modules A and B, which are mutually recursive, and we want them in positions where we can separately compile them. So they both have signatures and they both have definitions, which are sig A, sig B, and mod A, mod B, respectively. So the first thing we do is create a unit S. And what this unit has is, so you start with x equals dot dot dot. The dot 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 is it's the type components that are in signature A and B, and these are the type components that you need to that signature A and signature B need to refer to. So you put those in there, and now you have a unit that has all the type components of signature A, of A and B. All the type components are now there within S. So what you do after that is create two new units. And these units are separately compiled units. These units, you can do whatever you want with them. So for A, for example, you would have x equals new S, and then you link it using with, you link it to A equals the definition of A. So now the definition of A can get both signature B and signature A. And so it can freely refer to all the recursive, it can refer to itself, it can refer to B, and it can do what it needs to do as a recursive module. And you get the same result with this next binding here. This will give you the same result, except now it's just B's definition. And so if you want to combine them, you just link them together like so. But because they are separately compiled, you can use them as individual units, or you can link them to any other compatible units, so you can have different recursive units with different implementations, and you can freely toss them together. So it's a pretty powerful way of expressing separately compiled components for mutually recursive modules. The authors of Mixml also wanted their modules to be used as first-class values. So what they did was they introduced a new construct called unit signatures, also known as USIG. A unit signature basically describes the module when you're using it in a first-class context, when you're importing and exporting it. Just to go over the syntax a bit, for a unit signature, you start with mod, and mod is just an ML signature. There are no terms, there are no definitions. It just has the declarations and types you need. And then it's followed by a list of imports or exports. And what this does is it'll mark those as imports, and then the rest are treated as exports, and vice versa. So we saw the example earlier of where we made a unit of signature A's and B, and we then put it into a unit S, and then we would link it with A to get a unit that exported A. Now, if you wanted to come up with a unit signature for this module, we could write it as new S export A. So what S has is the imports of A and B, and it exports A and B. But we only export A, so it knows that it'll export the components of A, and it will not do anything with B. However, we can also say this, where new S, and all the components of B are imports, and everything related to A is an export. So those two are equivalent, and that's how we would make a unit signature for our mutually recursive module. So we discussed unit signatures, so now we can actually get into the first class units. So the new syntax that's introduced is the keywords pack and unpack. What these do is they allow you to basically use units in a first class context. This is made clear using the example we have here. So we make a variable tree map, and so if we have two modules, tree map and hash map, we assign them to two variables using the pack keyword. And then during runtime, we have the number of variables n, and based on that, we can either use tree map or hash map. And we use this with the unpack keyword, where we provide our module here based on based on the size, and then we provide either one of the two packages we made, and then we provide the unit signature. In this case, is just map, and it has import nothing, which means that everything in map is an export. So that's understandable from the context we went over in the last slide. And that is how first class units are implemented within MixML. So we went over the core features of MixML, and now we're going to go over some of the challenges the authors faced while writing the paper, specifically revolving around typing. So in this first example, we're going to go over bidirectional type lookup. And what this means in this example is you have f here, which is a function from int to bool, and you have a definition here, which is, a specification here, which is from int to type u, and u is an undefined type, and t here is undefined. So these are both undefined types. So this function will not hold true to its specification until t is refined to int, but we also have to get u refined to bool. So both the modules have to refer to each other bidirectionally at the same time to resolve their typing, and then only can the function definitions hold. So that's the bidirectional type lookup problem. So the next problem we have is cyclic type and term definitions. So we see here in this example we have two modules. In the first module, t is some type and u is some type. But the problematic line comes in when we say u is t, and here we say t is u. Now when we try to merge these two modules, we have some issues. We don't know how to resolve them. We have u as t, we have t as u, and u is type, so it's all over the place. And so the authors said that they would have to introduce something called equirecursive type checking. However, such an algorithm is not efficient in the general case, and so the authors have decided to simply reject this type of module linking in general, and it's just not allowed in MixML. So that's how they address that problem. So the next problem our type checker has to deal with is double vision, which commonly occurs when dealing with abstract types. So we see in the first example that we are defining a sealed module with type component t that is internally defined as an int. So we know that t is an int. It should follow that x.t is also an int, but clearly in the signature it's not. As a result, the programmer might have to expose t as an integer on the left-hand side of the module, but this would cause them to lose type abstraction. This problem is solved using a type checking system written by Dreyer, who is an author of this paper. His type checker utilizes a two-pass algorithm, the first being a static pass. The static pass computes the type components of the module. In this case, it will see the internal definition of t is an integer. Therefore, in the second pass, the full module is type checked, meaning it will check the external module, or this module. It'll check that that module is type sound when t is replaced with an integer, and it'll check that any occurrences of x.t are also type safe when they are replaced with an integer. In other words, based on the information on the right-hand side, we can type check any occurrences of information present in the left-hand side. This leads to our next problem, which is cross-eyed double vision. Here, we have function g, and if we want to type check this function, we have to deal with two instances of double vision. First, we have to check y is greater than 1. As we see, y is type u2, and so we have to know that u2 is equal to x.u, which is an integer. Next, to check the application of x.f, we have to know that this type x t1 or t has to be a Boolean. In other words, it has to go in this direction. So from our previous approach to double vision, we know that it'll check the right side, in which case we'll know that u, or u2, or x.u, is an int. However, the left-hand side won't be solved from our previous approach. So this takes us back to the slide we looked at for bidirectional type lookup. So for this case, we recall that we have a static pass, and then we have a second pass for our type checker. So this is solved by having a bidirectional type lookup in between the first two passes. So after the first pass is done, these modules will have a bidirectional type lookup where we learn that u2 is equal to x.u and t2 is equal to x.t, and their types are resolved. The next problem for the Mixin type checker is opaquely recursive types. So in this first example, we have a type int list that we want to type check. The Mixin type checker will see this definition and see the x.int list, and it'll say, hey, I've seen this before, and it'll say, that's this. And then it'll try to connect this x.int list to this definition of int list. And this type checker will fail because MixML will report it as a transparent type cycle. The MixML type checker solves this problem by intentionally invoking double vision by inserting a computationally irrelevant unit instantiation. What this does is changes the scope of the module declaration to a unit. MixML units are meant for separate compilation, so the MixML type checker will not try to connect this instance of x.intlist to intlist. Therefore, we won't have any cycle, and the type checker will proceed as normal. So as we delve more into the MixML type checker, it's good to know some of the syntax. Again, like what happened before, this is here for reference, and I will describe the syntax as it becomes necessary. Here is just a quick example of the type checker syntax. So we have this massive absolute unit here. And what it does is it has a module, it has a component A, which is a module, has a component R, which is a sealed module, which hides this implementation. This is all hidden, and this is all we see. Down here we have the semantic signature for this unit. So what it's saying is that, for all alpha and beta, for all alpha there exists a beta, this is the type locator. And what this signifies is that we're mapping alpha to a.t and beta to r.u. And then we have a function f, which takes alpha and goes to beta. and that function is being exported from the module. That is basically what is being said by the semantic signature, and it's a way of notation that makes it easier for the type checker to go through this unit. So now we can go more in depth about the type checking algorithm that's used in the Mixin type checker. For now, just ignore the blob of text on the right. We're going to be talking about the first step of the type checker, which is the static pass. The role of the static pass is to compute the static components of a signature before performing the full type check. It gathers the type exports of signatures, basically the concrete type definitions in the program. It doesn't care about any of the type of the dynamic components yet. These are handled in the template phase. The template phase is a lot more convoluted, and it deals with the non-determinism in the program and tries to handle all the dynamic typing. The goal of templates is to infer the shape of a module before it is type checked and then gradually fill in the template with more information as it is found. Basically, we want to provide a module and a template context, and the end result we want to see it return a type or a template signature S, a template type locator L, and a list of kinds for the export type names of the module, which is K. To expand a bit on template, we're going to look at an example template construction. In the first case, we're going to look at accessing the L component of module mod. Our module has a list of locators that is associated with the component L. It has a list of kinds, and then it has module templates for the L component and a bunch of other components that's given by L prime. However, we only want the L component. So our final template, when we call mod.l, will just look like the locators associated with the L component here, the list of kinds that are in our module, and then the module template associated with our L component. And we ignore all the module components associated with L prime. So that's a pretty straightforward example of template construction. Now we're going to look at a bit more complicated template construction. In this case, it'll be the link operation. So to start off, we have a set of common locators between both modules, which are disjoint from the module-specific locators given by L1 and L2. And we also have this side note that says L1 and L2 are disjoint. That's what this means. Next, we see that both modules have a list of kinds that are specific to each module. And each module has its own module template. Also notice that the environment for module 2 includes the module template for module 1 that is represented by X, because that's how the linking operation works. So first, let's go over the locators of our result. We'll start with these big terms we have here, these and these. This first one is the imports of mod 1 that are not present in mod 2, whereas this one is the imports of mod 2 that are not present in mod 1. So these two sets are basically the unique imports of mod 1 and mod 2, and these are added to the common imports of both sets, of both modules. Next, for the list of kinds, we just return both lists. Finally, for the actual module templates, we just combine the templates and return the result. And that is how we get a template for the link operation that we can then type check. So in conclusion, MixML provides expressiveness of ML modules with the benefits of recursive modules and separate compilation. It provides the best of both worlds without losing any part of either world. It also unifies ML structures and signatures into a single construct, which allows for more flexibility for programmers as well as simplicity and regularization in the language. In terms of future work, the authors would like to support OCaml-style applicative functions, type classes, and dynamic units. And they also want an implementation in an existing ML system. Their current prototype is a language that is based on MixML. It's not an actual ML dialect. And they want to have this actual implementation because it will raise more questions about MixML, specifically regarding potential optimizations, as well as concrete details of separate compilation and how that would actually work. So that is the story of how Rossberg and Dreyer mixed up the ML module system and made MixML.